Yes, so my name is Matthias Molin. I work in a part of the DevOps side of the business, more specifically in a group where we create tools that our customers use for producing real-time C++ applications. And today I'm going to talk about a new tool that was launched in December last year. It's called HCL DevOps Code RealTime. And the focus will be how users can use this tool to create C++ real-time applications with more abstraction, automation, analysis, and even some AI. But first, since I'm aware that not all of you are familiar with this domain, I want to give you 4 examples of machines and systems that our customers use our tool for creating the software for. First example is a machine that creates credit cards. So what you see here as the first picture is a machine that gets a sequence of plastic cards arriving at one end, and in the other end it spits out ready-to-use credit cards. So obviously this machine needs software that control many things that need to happen very quickly. For example, you need to make a hole in the plastic card, and then you need to glue a chip in that hole. You need to print the cardholder's name and maybe the logotype of the bank, and so on and so forth. Some of these tasks can be done in sequence, while others can be done parallelly. For example, you may be able to make the hole for the chip at the same time as you print the cardholder's name, but obviously you can't glue the chip before you have made the hole. So there are some constraints that the software needs to respect. And the more things you can do in parallel, the faster the machine becomes and the happier the customer is. Second example may look completely different, but actually has lots of in common if you look at it on the software side. A telecom system. So when you make a phone call with your mobile device, the chance is very high that that phone call gets routed through software created by our tool. In telecom, there are lots of phone calls going on in parallel, of course, independently of each other, but also within each call, they have to adhere to the telecom standards, which typically involve many sequential handshaking procedures. So also here, there is a mix of sequential and parallel activity in the software. For these 2 first examples, time is important, but if there is slowness anywhere, the worst thing that happens is that machine goes slowly or some phone call maybe is dropped. But there are also examples where time is of critical essence. So we have customers that use the software for creating a defense system or medical devices. And in that case, a too slow response for an event can actually mean the difference between life and death. And the 4th example is maybe the most easy to relate to. This is a coffee machine as an example of a consumer product that also has this kind of software inside. So when you push the button on that machine to get a cup of coffee, there are many things that need to happen. And once again, some things can happen in sequence, other things can happen in parallel. So what is common between the software in all these examples and many more is that it's event-driven, meaning that the software consists of objects that communicate by sending messages. It's stateful software, meaning that each object in this software has a state machine or can be described by a state machine. And it's real-time, meaning that the system must respond in a timely manner. And exactly what is timely, of course, depends on application. So let's take the coffee machine as an example and look inside what kinds of object we could expect to find in its implementation. So for example, there could be an object temperature sensor responsible for reading the water temperature. There could be another one controlling the boiling process. It may be a third object that controls the display where user can choose the beverage he wants to have and also see the progress of that beverage being produced. And each of these objects operate autonomously with a well-defined responsibility. But of course, they need to communicate. So for example, a water boiler cannot know when to turn off heating the water unless the temperature sensor gives it the current temperature of the water. So these messages that are sent back and forth, they may or may not, depending on need, carry some data. If we look at one of these objects, let's take the water boiler, we can see that it has a state machine which describes how this object changes over time. So it may start, for example, in some ready state. Then at runtime, it receives messages from other objects which get queued, but at some point, these messages are dispatched. And when that happens, a transition between two states can trigger in the state machine. So it goes from one state to another. And that transition can then run some piece of code, which basically can do anything. But in particular, that code can send out objects to other or messages to other objects. So what we essentially have in these kind of applications is a network at runtime of connected objects that communicate by message exchange, and each object is described by means of a state machine. So now that we know a little bit about how these applications work, let's look at the technology used for creating them. So a few decades ago, maybe not a few, but a couple of decades ago, C was the dominant language here. But nowadays, I think almost all people use C++ for creating these applications. The applications also need some operating system, of course, and in many cases that can be a variant of a desktop operating system like Windows or Linux. But in some cases, people prefer real-time operating systems which give even more or better performance to these applications. And as you could have guessed from my examples, many of these applications can be categorized as embedded applications. Sometimes they also involve some communication with the cloud service or internet service. In that case, we maybe would have called them Internet of Things or IoT application. But there are also examples where it's not really any of these. For example, telecom software can run on a quite powerful server somewhere in network, and I wouldn't call those applications neither embedded nor IoT. It's also quite common in these applications that customers need to create more than one variant of the application from the same sources. And that typically depends on what hardware is available. So the same telecom software, for example, can in some cases be run on an environment where there is quite powerful hardware available. And then the software should scale up and take advantage of all that hardware. While in other cases, same software may run in a much more resource-constrained environment where it has to the opposite, scale down, so that it can fit within the resource constraints. Tracing is another important technology for troubleshooting and debugging these applications, because with a C++ debugger, you can of course debug each object in isolation, but it's hard with a C++ debugger to get the overall picture of how these objects communicate, and especially if there is some problem in the event sending, so that messages are not sent or received in the order that you expect. So assume you are a developer and you get the task to create a software of this kind. Where do you start? Can you just grab your C++ compiler and IDE and get started coding? Well, of course you could, but you should maybe wait a little and think about other people that have done this in the past. Because it turns out this is not a new problem domain. Already in the early 90s, people realized that coding these applications or these kinds of applications manually was time-consuming, error-prone, and very boring, because there's a lot of repetitive code that has to be written for these state machines, and in C++ or C, you don't have any concepts of a state machine. You have to code them yourself in lower-level constructs like switch statements. So in the tool I'm going to talk about today, Code RealTime, is actually the fourth generation of a product that started its life in the early 1990s, when a Canadian company called ObjectTime produced a software tool called ObjectTime Developer. The big invention here was that they introduced a domain-specific language called ROOM, Real-Time Object-Oriented Modeling Language, which allowed the user to raise the abstraction level from C or C++ to use things like state machines, capsules, ports, those high-level concepts that are perfect for describing these applications at a higher level. That tool was later transformed into ROSE RealTime, which is the second generation of the product. This happened when Rational acquired ObjectTime. I think it was around 2000, year 2000. And then the decision was taken also to make it a UML tool, the first version of UML. We actually still have many customers using this, and that proves that this software is kind of sticky. Once you have started to use it, you're a bit hooked. So for good and for bad, because it also means that customers can use 20 years old software that we ideally would not like to support anymore. But these customers also have very long life cycles of the product, which require them to stay on old versions sometimes. Then around year 2007, 2008, IBM had acquired Rational and decided to create the third generation of the product based on the by then quite new and popular Eclipse platform. And then also they upgraded to use UML 2, which was the latest UML standard at the time. This version is also used by many customers still. And in 2016, when HCL joined this IPP agreement with IBM, HCL created its own variant or branded version of this product called HCL Artist. But in December last year, this product was renamed to DevOps Model RealTime. And one reason for this rename was that at the same time, we launched the first version of DevOps Code RealTime. So we wanted the name to reflect the relationship between these products. And the big new thing in Code RealTime, as you can hear from its name, is that it's a more code-centric approach to solving this problem, while previous tools were a bit more model-centric. There is also a difference that while Model RealTime runs on Eclipse, Code RealTime runs on more modern IDEs such as Visual Studio Code, Eclipse Thea, or even as a standalone web application. So why did we create another tool? That's, of course, a very legitimate question to ask. Well, the IDE situation was, I think, the driving force. We wanted to attract users that don't like or cannot use Eclipse to also be able to use our tool. But we also wanted to improve the usability for C++ developers. Tools like Eclipse and UML are not really designed for C++ developers. And in particular, we wanted to provide a more text-centric way of working as opposed to more diagram-centric. And we also wanted the code generation to be much more automated, so it kind of happens in the background without the user having to do any specific command to get the generated code. And this has led us to a situation where we have a tool now, the Code RealTime, that supports working at 3 different abstraction levels depending on your task. So at the highest abstraction level, we have graphical diagrams that you can see in the top of this picture. Here you have few details, but on the other hand, it's very easy for someone to understand what this does, even if you don't have any software programming experience. And this is important because many of our customers work in cross-functional teams where software engineers have to work together with electrical engineers or mechanical engineers, even chemical engineers. And they all must be able to, at some level, understand what the application is doing, even if they don't know how to code C++. The middle layer is a textual language, which we call art. This is also the storage format, so it's the art files that you put into Git or your SCM system. It has the same abstraction as the diagrams, but with a texture syntax, it's much easier to edit in a text editor. And of course, you have all the support for syntax highlighting and content assist and all those features that you expect from a modern IDE these days. And then at the lowest level, we of course have the C++ code because at the end of the day, this is what you want to get at. This is the code that gets compiled and run. It has low abstraction level, lots of details, but sometimes you need to work even on that level, of course. But I would argue that even an experienced C++ programmer usually prefer to think about the state machine in the graphical notation rather than reading this nested case switch statements that you see in the bottom here. So some benefits with picking a textual language. Well, I already mentioned that there are editing ergonomics that are better with text. Developers are often used to textual languages from coding. Graphical languages can be nice to look at, but can be a bit cumbersome to edit and require mouse, which can be an ergonomic problem. And also at the heart of modern IDEs, such as Visual Studio Code, is a very powerful text editor. Many things that is graphical in Eclipse, for example, is basically as a text file in VS Code. It's also the fact that developers don't just use one tool for creating applications. They use a bunch of tools. And many of these tools are based on text files. So for example, if you want to search for something, you want to run a compare merge operation, If you use Git, you probably use Git pull requests, which also requires textual notation. And in the past, we have had to create our own tools for supporting these workflows, mainly because the way Eclipse works and that we did use proprietary storage format. But we really would like to avoid that because users are used to these tools and this is not what we want to compete with. So by having a textual format, user can pick any of his favorite tools that he already is comfortable using. And the third benefit, which I must admit we'd had no idea of when we started this work a few years ago, but it has emerged now as a very important thing, and that is the generative AI solutions that are available for developers. Here I'm thinking mainly about GitHub Copilot, which we have tried, but there is also watsonx Code Assistant from IBM and a few others, and they all work best with the textual input. The LLMs behind these AI solutions, they take text both as input and output, and some of them recently support refining the results using knowledge bases or retrieval augmented generation. And in that case, you can provide additional information to it, which also is a set of text files. So it's fair to say that these days text is king. So looking at this art language that is at the center of Code RealTime, this is a domain-specific language for creating reactive systems that consist of communicating objects with state machines. It might be a new language from the syntax point of view, but it's actually old in the sense that it builds on the concepts that were present already in the predecessors UML RealTime and Room, which has already been used in industry and proven with a good track record for more than 30 years. It is, like I said, a textual language, but it still have the graphical diagrams, which are important for getting the good overview and abstraction. And another thing that we were careful doing when we designed it was to make it a pure extension of modern C++. So UML, for example, has a quite big overlap with C++, which also is always a source for confusion for new users. But here we wanted to have a pure extension, which means that we can have a small language with an intuitive syntax and no overlap with C++. So in this screenshot, you can see some of the examples how an art file could look like. We have the high-level concepts of capsules, state machines, ports, and there are a few others, but in total, I would say around 10 concepts. So it's a rather small and easy language to learn. And then these blue boxes here show the C++ code that you can embed in these art files. And you use C++ for including header files, so you can reuse any legacy C++ code you have or something that you prefer to code manually. You also use C++ for writing the code that should happen when a transition is triggered, or an expression that defines the condition for when a transition can trigger. And you also use C++ for defining types. So there is no overlap at all. So those things that C++ is good at, we let C++ do, and the rest we do with art. So looking at the central concept of the language is the capsule, and this is an active object that encapsulates a number of things. And the word capsule actually comes from the word encapsulate. So similar to a C++ class, a capsule can have data in the form of C++ member variables. It can also have passive behavior in the form of C++ member functions. Those are, however, always private and protected and rarely public due to thread safety reasons. But then in addition, and contrary to a C++ class, it can have an active behavior in the form of a state machine, which describes how this object changes over time. It can also have ports that are used for sending and receiving messages from other objects. And those ports are typed by protocols, which define the valid input and output on each port. So a protocol is basically a set of events, and each event can define what data can be sent to that port. Then you can connect these ports statically or dynamically to other capsules. The benefit with doing it statically is that you get a very nice graphical description of what parts or components your application consists of and how they can communicate. But sometimes the system is so dynamic, so you cannot do this statically, but you have then to establish these connections dynamically at runtime. And also important is that these state machines can become very, very complex and big as time goes by. And then it's important to be able to refactor and break them down into smaller parts. So you can take parts of a capsule state machine and create another capsule from it, which you then can use as a part of that first capsule. So this is a way to manage the complexity. There are 3 diagrams supported in Code RealTime. State diagrams are the most commonly used. So here you see the state machines, which consist of state, pseudostates, and transitions. We support nested states, which means that if you have a state with substates, you get this little yellow expand collapse button that you can use for deciding if you want to see those nested states or not. And of course, you can nest at as many levels as you like. We also allow a capsule to inherit from another capsule as a way to specialize or refine or extend a base state machine in the derived capsule. That can often be quite useful to reuse code. And like I said before, C++ code is used for deciding what should happen when a transition triggers, and also you can add code that is run when you enter or exit a state. Structure diagrams is also very useful. They show the parts in your application and how they can communicate by means of connectors. So this is a view that you rarely can easily see in a C++ program, where communication is rather implied. You have to read all the code and kind of build your mental picture around what components exist and how they communicate. And here you can see it graphically instead. And of course, here also you can use inheritance if you want to refine a generic structure. And we also support class diagrams, which are very similar to the class diagrams of UML, where you can show graphically the relationships between types in your application. So with that, it's time to show a quick demo of Code RealTime. And here I have installed a Code RealTime extension from the Visual Studio Marketplace. So we publish the product on the marketplace so people can just download it from within VS Code. Then you get the community edition, which is a free non-commercial edition with some limitations, of course, which are mentioned down here. So people who have tried this and like it will hopefully then contact HCL or IBM to buy the commercial edition. But it's fully functional for private projects or for universities and people like that to try and use it. And if we look here in this Explorer view, we have here, typically here you would put projects or folders that contain the different modules of your application, but here I have instead imported a few separate small sample applications. Now we'll use one here as a way to demo the tool. So this is a traffic light logic where there is a user interface implemented in Qt. And the good place to start when you want to learn a new application is this file called .tcjs. So this is a transformation configuration file, which is a JavaScript file that contains properties that describe how this application should be translated from Art to C++ and then compiled into an application. And there are many defaults, so in the simple cases, you don't need to specify so many things, but at least you need to specify 2 properties. The target folder, this is the location where the generated C++ code gets generated. And as I mentioned before, we have code generation running on the fly in the background. So it means that as soon as you have created this, you actually have all the generated code available to you in this folder. And the second property is what is called a top capsule. This is like the main function of a Java or C++ program. It's where the application starts to run. So when the application starts, it creates one instance of this capsule called TL system, and that state machine then starts to run, and it's from there that everything else will happen. So if we navigate to this capsule, we can see the art file for it, which we of course can read and edit here, but we can also right-click and open the diagram to get the graphical description of it instead. So here we see this nice high-level overview, what components our application consists of and how they can communicate. So we see we have a pedestrian light, we have a user interface implemented in Qt, and we have a traffic light, and all these 3 components need to communicate with each other. Then we also have a pedestrian or push button, which the user can push or pedestrian can push if he wants to cross the street. And then we need to send a message to the traffic light to make sure that the traffic light is red when the pedestrian is crossing the street. From any of these capsules, we can navigate to the state machine that describes how this object behaves. So let's open the state machine of the traffic light and make it slightly bigger here. So the state machine works like this. It starts on the initial state, and then it goes to this first state, which in this case is cycle light. And here you see a blue little icon, which means that there is C++ code running here when this transition is taken. And here you see that what happens is that we write a log statement to the console, and then we are setting a timer that will time out once every 2 seconds. And that is a timer that drives this traffic light through the red, green, and yellow states in a loop. Then when the pedestrian pushes the button, this transition here called ped request will be taken, and it will then take the state machine to the pedestrian crossing street or state, where the traffic light, of course, should be red. So here it stays for a while, so the pedestrian can safely cross the street, and then it goes back again to the cycling of the states. So these composite states you can collapse if you're not interested in the details, and that can be useful if your state machine is complex, but in this case, we might be simple enough to look at everything expanded. So I also like to show you the C++ code for this. So if we, for example, take this initial transition and you do open generated code, here you get to the generated code. And you may have seen that the art file corresponding to this state machine was a bit more than 100 lines of art code. But in C++, the same thing is more than 600 lines. So now you maybe realize that typing this manually is quite tedious, especially this function that defines the state machine logic is quite boring and error prone. And here I only have a state machine with less than 10 states. We have customers that have state machines with thousands of states, and then it's not really feasible to write this by hand. So then when you have your generated code, you can just build and run it. And in many cases, it's enough to right click here on the TC and do build or run. But in this case, I have chosen to use another IDE where I have developed a user interface for this application. And this is the Qt creator from Qt, which is popular, for example, for creating UIs for C++ applications. So here I have imported the generated code in these folders. These come from Code RealTime. And then I have written in addition a few more classes myself to implement a simple UI that visualizes how these components work at runtime. So I can compile and run this application, and then you get this visualization that shows the current state of the traffic light and the pedestrian light. When we push this button here, if you remember the state machine, it now goes to the red state, pedestrian state machine goes to the walk, and then back to stop. And then after a while, it starts cycling the light again. And here in the console, we see the printouts from the application. So creating a UI like this can be quite useful when prototyping, and also sometimes the hardware that this software is going to operate may not be available initially because that might be developed in parallel, and then you can do simulation and getting your software right by writing a simple UI for it. But we don't have any support for creating that UI in Code RealTime, so that's why it's useful to integrate to another IDE like Qt in this case. I can also mention here that if we open these, both the C++ file and the art file at the same time, we can put them next to each other. And if we take one of these, we can take the initial transition here, and we navigate to that in the generated code. If we make a change here, like changing this, it immediately updates here in the generated code. So this shows that code generation happens on the fly as soon as we change something. But we can also do the opposite. So if I remove that character again and save, you see the corresponding art file is updated here. And this is useful because if you make a mistake which leads to a compilation problem, the compiler will of course point you at the generated code, and then you can fix problems directly here in generated code, and they are automatically synchronized back to the art file, which you then will put into Git. And you can even, if you make a change here, like adding a new state, you can, if you prefer to work graphically, you can do that. Then we create the state here. We added it also here in the art file, and actually also in the C++ file here. So these three abstraction levels are kept in sync so that it's consistent all the time. But this view, the C++ view and the diagram, they are synthesized from the art view. So this is what you really put into version control. So now I'd like to return back to the slides and show this slide, which summarizes the value that Code RealTime provides. It's basically, you can describe the value by 4 words that all start with A, by accident or by chance. It's about abstraction, automation, analysis, and some AI. So abstraction, of course, these high-level concepts that I've shown you, the graphical diagrams, and a few others, that they provide a better abstraction than what you get from a more low-level language like C++. Automation, here the most important feature is, of course, that code gets generated automatically. And there are some other features also in this area. For example, the solution to the problem I mentioned in the beginning, to create more than one variant of an application, is supported by something called build variant, which basically is a way to automate the build using high-level build settings. And there are a few others also. So I didn't show in this brief demo the analysis capabilities, but actually when you make modifications to your art files or your transformation configurations, we run a large number of semantic validation checks as you type. And these checks can find problems and potential problems early while they are still cheap to fix. And for example, we can detect the build setting inconsistencies, which could lead to runtime surprises otherwise. There is also quite a big need for analyzing the result of tracing. So when applications run in production environments, they can produce tons of traces that have to be analyzed. And this is an area where we don't have so good support currently, but we are hoping to join a European Union funded research project that will start in Q4 if it gets accepted. It's called Mona Lisa. And here we will work together with some universities and some other companies that are in this domain to try to use AI for analyzing and querying application logs. For example, it would be very useful if operators can use natural language for querying the application logs, so they don't need to know a formal language that you may need to do today. But the AI part that can be used already today is to use a textual language Gen AI dev tool like GitHub Copilot or Watson Code Assistant. Although so far we have tried only GitHub Copilot, and that can really help you in many scenarios where when you are developing your application. And I like to show you some of these scenarios in a video, and I choose to make a video actually because when I try this, sometimes GitHub Copilot response times have been a bit slow recently, so I didn't want any slowness in this demo. So let's look in this recording instead on a handful of scenarios I tried. So the first scenario is perhaps the easiest one. Here we have just selected a piece of C++ code, although it's embedded in an art file. We want Copilot to explain what does this C++ code mean. And this is no difference. Let's see why it doesn't show up. Yeah. So this is no different than if this C++ code would have been part of a C++ file. So GitHub Copilot really doesn't care about where the code is located. It invents something about what this art could mean, which is, I guess, a bit of a hallucination because it actually isn't an acronym for anything. But despite that, it provides a quite accurate description of what these 4 lines of code does. And it's obvious that when you read this description that it has analyzed the runtime library header files that describe these functions, because the LLM couldn't have been trained on this code since it's not available anywhere on publicly on internet. Second example, here we make it a bit harder for Copilot. Here we select an art file And since art is a domain-specific language, which was launched in December, it's highly unlikely that LLM of Copilot has ever seen an art file when it was trained. But still, it's able to produce a surprisingly accurate description of what this art file does. So you see, it understands here that what parts it contains and how these parts communicate, and it can also describe a bit of the state machine. And even if this might not be 100% correct, it's still fairly accurate description of how this application behaves. The third example is similar, but here we use Copilot for generating documentation for an art state machine. So we selected the state machine and we asked Copilot to generate documentation. And this documentation is also correct. Maybe it in some cases is a bit too detailed, or at least in my opinion, but it can be a great starting point to start with this documentation, and then you can change it yourself to slightly add more detail or remove some detail that you think is necessary. Next example is a bit more complicated. Here we write in natural language and ask Copilot to perform a refactoring. So here, Copilot is supposed to change some parts of my state machine so that all states it contains will be prefixed with a prefix. And this is challenging because previously it just kind of suggested things, but here it actually has to update and make sure that the result is correct. And it actually managed to do that, as you see here. And this example here is related to this semantic validation I talked about. So we can right-click on this and ask Copilot to explain what does this semantic validation mean. And this is also interesting because these validation rules are, of course, not known by Copilot, but just by analyzing the context, it's able to provide a quite accurate description for the user what this problem means and how it can be solved. And it even is able to provide an example in correct syntax in this art language, how you use entry points, which is the key for solving this particular validation problem. And the last sample here, we ask Copilot, we select a line of C++ code, and we ask Copilot to change this code so that it sets a periodic timer instead of a one-shot timer. This is also challenging because these concepts of a periodic and one-shot timer are highly code real-time specific and not something that it really could have seen when being trained, but it correctly suggests that the user is supposed to change from the API inform in to instead use inform every. So these were some of the examples of the Copilot usage that is available already now and can be used by users. And finally, recently, there was a new version of Copilot released. It's called the Enterprise Edition. I think it was end of February. And they have a new key feature, which they call knowledge bases. This allows Copilot to take additional input, which can be used to improve the quality of the text response. And this is known as a knowledge base, which can be a set of documentation, samples, test cases, basically whatever, that was not available at the time when the LM was trained. And there can be two reasons why it was not available. One, of course, because it was not available at that time. But second, because it's proprietary. So it's not something that is publicly available for Microsoft to use in the training. Unfortunately, we don't yet have access to this version. So in HCL, we only have the business edition. So we are working with IT to see if we can at least get some trial from this enterprise edition and do some experiments, because we have all the information ready to create such a knowledge base, but we would like to see how much better the response becomes when doing that. And in particular, providing the documentation, product documentation should, at least in theory, give a very good quality of the response. And as you can see, this is what is usually called RAG, or retrieval augmented generation, which is nowadays, I think, something that every LLM solution for developers, they are trying to have something like this. And with that, I've come to the end of my presentation, and I think there is time for some questions. Okay, so there is question here about other languages like Java and Python. So the answer right now is that we haven't looked at this at all. And the main reason for that is that our customers are using C++. So in the past, there were some product versions that supported Java also, but the market for creating real-time software in Java is very small, or next to nothing, I would say. So we decided it was not worth the investment. And Python, I haven't even heard anyone writing this kind of real-time applications in Python. It would be possible, most likely. We had a PhD student some time ago who did a proof of concept in JavaScript, and it was possible. But I think the market is a bit lacking, so we haven't looked at that. Yes, state machines are, of course, used outside. So it would be possible if we would address a more general state machine usage, then I think it makes sense to look at more languages. But in our case, where we have an existing runtime system that is specifically adopted for these kind of C++ applications, that is why we have focused on C++. Next question here about Thea, if there is much adoption of that beyond Ericsson. Yeah, here I must say I'm not sure. So Thea, for those of you who are not familiar, you could describe it as an open source version of VS Code. It shares some of the components, but there is a community around it, like Eclipse. And Ericsson is one of the founders, and of course they are using it. And honestly, that was one of the reasons why we support it too, because Ericsson is one of our largest customers. So I don't know. I see some companies in the Thea meetings I'm entering, but I don't know, to be honest, how much they use it. And I have a feeling that VS Code is a really hard competitor for Thea, actually. Another question, the relationship between IBM and HCL, and if it still is an IP deal. And yes, the answer is yes. This is still within the IBM HCL IP agreement. So there is both an HCL and an IBM branded version of this product, just like for Model Real-Time. Yeah, so does it provide automated checks or mean to check against memory leaks? Yeah, so the memory leak checking, that I think there are already quite good tools for that at C++ level. So the checks we are focusing is more like on the same abstraction level as the state machines. So we are able to detect things like deadlocks or states that are not used or other things that could lead to problems.